The ice cracked. Not from above, where Arctic wind had carved pressure ridges across the frozen sea for 10,000 years, but from below. Something massive was rising through water so cold it should have been solid, pushing upward with force that shattered ice nearly 2 meters thick. NATO surveillance aircraft circling over the Barents Sea had detected unusual seismic activity, patterns that didn't match natural phenomena or known Soviet submarine operations. When the ice finally broke, splitting apart in jagged fractures that spread for hundreds of meters, what emerged was beyond anything Western observers had prepared for. A sail rose from the dark water, massive and angular, reinforced with steel thick enough to punch through Arctic ice without hesitation. Then the hull surfaced, black and enormous, water cascading off a structure so large it seemed more geological formation than machine. The reports that reached NATO naval intelligence that winter morning in 1981 contained measurements that analysts initially rejected as errors. No submarine could be that large. The laws of physics, the limitations of materials, science, the practicalities of submarine warfare all argued against it. But the surveillance photographs didn't lie, and neither did the sonar readings. The Soviet Union had built something unprecedented, and it had just announced its existence by smashing through the roof of the world. This was the Typhoon-Class Submarine, though the Soviets called it Project 941 Akula. It was the largest submarine ever constructed, a distinction it maintains decades later, and its appearance forced Western navies to reconsider fundamental assumptions about submarine warfare and strategic deterrence. At 175 meters long and displacing 48,000 tons when submerged, the Typhoon dwarfed every other submarine in existence. It was longer than 2 American football fields, wider than a 4-lane highway, and heavier than many surface warships. Yet, despite its enormous size, it could move through the ocean depths with stealth that made detection difficult and tracking nearly impossible. It represented the apex of Soviet submarine engineering and perhaps the most terrifying expression of Cold War nuclear deterrence ever deployed. The story of the Typhoon began not with engineering blueprints, but with strategic calculations made deep within Soviet military planning circles during the height of Cold War tensions. American ballistic missile submarines patrolled the world's oceans, carrying Trident missiles with ranges exceeding 7,000 kilometers, allowing them to strike Soviet territory from positions far from Soviet shores, where detection and interdiction were nearly impossible. Soviet submarines, by contrast, carried missiles with significantly shorter ranges, forcing them to operate closer to American coasts, where they were vulnerable to American anti-submarine warfare capabilities that were among the most sophisticated in the world. Soviet naval planners recognized this vulnerability as a critical weakness in their nuclear deterrent strategy. They needed a submarine that could patrol in waters near Soviet territory, protected by their own naval and air forces, while still possessing the to-strike targets deep within the United States and its allies. The solution required breaking every conventional rule of submarine design. Build a vessel so large it could accommodate intercontinental ballistic missiles over 16 meters in length, with ranges exceeding 8,000 kilometers. Design it to operate primarily beneath the Arctic ice cap, using the permanent ice cover as both concealment and protection. Give it revolutionary twin-hull construction for unprecedented survivability. Install accommodations that would keep crews mentally and physically capable during patrols lasting 3 to 4 months in the most isolated environment on Earth. The Typhoon would be a missile platform, an underwater fortress, and a statement of Soviet engineering prowess that would force the West to acknowledge Soviet capability to match or exceed anything American shipyards could produce. The Rubin Design Bureau in Leningrad received the assignment in the mid-1970s, tasked with creating what would become the most ambitious submarine project in naval history. Chief designer Sergei Kovalyov, already renowned for previous submarine designs, assembled a team of specialists who would spend years solving engineering problems that had never been encountered before. The sheer size of the proposed submarine presented challenges that existing technology couldn't adequately address. A conventional single-hull design at this scale would be structurally vulnerable, unable to withstand the enormous pressure at operational depths without becoming prohibitively heavy. The solution Kovalyov developed was revolutionary and counterintuitive. Instead of one massive pressure hull, the Typhoon would have two complete pressure hulls running parallel through the length of the submarine, each 5 meters in diameter, connected by reinforced passages and surrounded by an outer hydrodynamic hull that gave the submarine its distinctive bulbous appearance. Each pressure hull functioned essentially as a complete submarine. One hull contained the command center, navigation and communications systems, reactor control stations, and primary crew quarters. The other held weapons control systems, auxiliary machinery, backup systems, and additional crew spaces. This redundancy meant that catastrophic damage to one hull wouldn't necessarily doom the entire submarine, a survivability feature that no other nation's submarines possessed. Between the two pressure hulls, in the space separating the inner vessels from the outer hydrodynamic shell, were mounted 20 massive missile tubes, each containing an R-39 RIF intercontinental ballistic missile. Each missile carried 10 independently targetable re-entry vehicles, meaning a single Typhoon submarine possessed the destructive capacity to strike 200 separate targets with nuclear warheads. The arithmetic was sobering. One Typhoon carried more destructive power than all the explosives detonated during World War II, including the atomic bombs dropped on Hiroshima and Nagasaki. The nuclear propulsion system consisted of two OK-650 pressurized water reactors, each generating 190 megawatts of thermal power, connected to separate steam turbines that produced a combined output of approximately 50,000 shaft horsepower. This enormous power plant could propel the submarine's massive bulk through the water at speeds exceeding 27 knots when submerged, faster than many surface warships and comparable to smaller submarines despite the Typhoon's vastly greater displacement. The reactors used enriched uranium fuel assemblies designed to operate for decades without refueling, meaning the submarine's operational lifespan would be limited by mechanical wear and crew endurance rather than fuel availability. The propulsion system incorporated sophisticated noise reduction measures, including resilient mounting systems that isolated machinery from the hull, rubberized anechoic coatings that absorbed active sonar pulses, and careful hydrodynamic design to minimize flow noise and cavitation. Construction took place at the Sevmash shipyard in Severodvinsk on the White Sea, one of the Soviet Union's most secure and capable naval construction facilities. The shipyard was surrounded by restricted military zones with access controlled by multiple security checkpoints. Workers required special clearances and lived in closed cities where contact with outsiders was severely restricted. Western intelligence agencies knew something significant was under construction at Severodvinsk through satellite reconnaissance and signal intercepts, but the full scale and capability of the Typhoon remained unclear until the first boat completed sea trials and was photographed during Arctic operations in 1981. The images shocked Western naval analysts who had been tracking the program. The submarine was far larger than their most pessimistic estimates, representing a capability leap they hadn't anticipated. The first Typhoon, designated TK-208, completed initial sea trials in late 1981 and entered formal service with the Soviet Northern Fleet in 1982. 5 additional submarines would eventually be laid down, though only 4 would achieve full operational status. The final 2 hulls were never completed due to the enormous costs involved and changing strategic priorities as the Cold War entered its terminal phase. Each Typhoon cost approximately 300 million rubles to construct, an astronomical sum that strained even the massive Soviet military budget. Individual components were built in factories across the Soviet Union and transported to Severodvinsk for final assembly, a logistical undertaking that involved thousands of workers and specialized facilities scattered across multiple Soviet republics. Life aboard a Typhoon was profoundly different from the cramped, austere conditions typical of most submarines. The unique twin-hull design, driven by the need to accommodate enormous missile tubes while maintaining structural integrity, created internal volume that would have been wasted in a conventional design. Soviet naval architects, recognizing that crew morale and mental health were critical for extended deterrent patrols lasting months, utilized this space for amenities that other submarines couldn't accommodate. Crew quarters included individual sleeping compartments for officers and small shared cabins for enlisted personnel, a dramatic improvement over the hot bunking arrangements where sailors shared beds in rotating shifts that were standard on conventional submarines. The reported inclusion of a sauna, small swimming pool, and gymnasium, while perhaps embellished in some Western accounts, reflected genuine Soviet commitment to crew welfare. The galley was equipped to prepare varied meals using provisions stored in the extensive spaces between the pressure hulls, and recreational facilities included a library and areas for off-duty relaxation. But no amount of comfort could fully mitigate the psychological weight of operating a submarine designed for nuclear apocalypse. The crew of 160 officers and enlisted men lived surrounded by enough destructive capacity to eliminate civilization, understanding that if they ever received authenticated orders to launch their missiles, it would mean the world they knew had effectively ended. Training emphasized absolute discipline and rigid adherence to launch procedures, with multiple redundant safety systems ensuring that firing nuclear weapons required coordinated actions by several officers using authentication codes that changed on encrypted schedules. Two-man control prevented any individual from launching weapons alone. Physical keys had to be inserted simultaneously in stations separated by sufficient distance that one person couldn't reach both. The burden of this responsibility affected everyone aboard, from the captain who bore ultimate authority to the youngest technician maintaining the reactor cooling systems. The operational profile of Typhoon submarines was fundamentally shaped by Arctic geography and Soviet strategic doctrine. Unlike American and British ballistic missile submarines that patrolled the open Atlantic and Pacific Oceans, often operating near adversary coastlines where their missiles could reach inland targets quickly, Typhoons were designed to operate primarily beneath the polar ice cap in waters relatively close to Soviet territory. Soviet naval doctrine called for bastions, heavily defended patrol areas where Soviet anti-submarine forces could prevent NATO intrusion, while their ballistic missile submarines maintained continuous deterrent patrols. These patrol zones in the Barents Sea and beneath the Arctic ice gave Typhoons secure positions from which their long-range missiles could reach targets throughout North America and Western Europe, while remaining under the protective umbrella of Soviet air defense and anti-submarine forces. Operating beneath ice required specialized capabilities that no other submarine possessed to the same degree. The Typhoon's sail was reinforced with exceptionally thick steel plating capable of smashing through ice several meters thick without sustaining structural damage. Upward-looking sonar arrays continuously mapped the ice overhead, identifying polynyas, natural openings in the ice where the submarine could surface safely, or areas where the ice was thin enough to penetrate forcibly. When circumstances required breaking through solid ice to reach the surface, the submarine would rise slowly, using its enormous mass and reinforced sail to crack and then shatter the ice sheet, creating an opening through which missiles could be launched if war orders came. Tests demonstrated that a Typhoon could break through ice exceeding 1 meter thick, though thinner ice was preferable to minimize stress on the hull structure and avoid creating noise that might reveal the submarine's position. Western navies devoted enormous resources to tracking Typhoon movements, deploying their most capable attack submarines to shadow Soviet ballistic missile boats whenever possible. This underwater stalking game beneath the Arctic ice represented some of the most dangerous military operations of the Cold War. Submarines from opposing sides maneuvered in close proximity in an environment where visibility was zero. Communication with surface forces was impossible, and any miscalculation could trigger incidents that might escalate beyond anyone's control. Soviet attack submarines and maritime patrol aircraft provided protective screens around Typhoon patrol areas, while NATO submarines and surveillance systems attempted to penetrate these defenses to maintain continuous awareness of where Soviet strategic submarines were operating. The imperative was clear. In any crisis, knowing the location of enemy ballistic missile submarines could mean the difference between effective deterrence and catastrophic surprise. Several incidents during Typhoon operations brought Cold War submarine tensions uncomfortably close to potential disaster. In 1986, a Typhoon experienced a serious reactor cooling system malfunction while on patrol deep beneath the ice, forcing emergency procedures that could have led to core damage if not resolved within a narrow time window. The crew, drilled extensively for such contingencies, managed to restore cooling flow and prevent a reactor meltdown, but the incident highlighted the inherent risks of operating complex nuclear systems in the hostile Arctic environment, far from any assistance. Other encounters saw Typhoons and NATO attack submarines maneuvering at close range, situations where aggressive actions or misunderstood intentions could have resulted in collisions or even combat. Each close call reinforced the reality that deterrence, while effective, operated on a knife's edge, where accidents or miscalculations could have consequences far beyond the immediate incident. The submarines embodied deterrence in its most fundamental and unsettling form. Their existence ensured that any nuclear attack on the Soviet Union would be answered with overwhelming retaliation, making such an attack effectively suicidal for any aggressor. This concept of mutual assured destruction, the grim calculus that prevented nuclear war by making it unwinnable, depended entirely on weapons systems like the Typhoon remaining invulnerable and continuously operational. Soviet naval commanders understood that as long as at least one Typhoon was on patrol, undetected somewhere beneath the ice, the Soviet Union's nuclear deterrent remained credible and effective. This knowledge profoundly shaped American strategic planning, forcing acceptance that no conceivable first strike could be completely successful as long as Soviet ballistic missile submarines survived to execute retaliation. But maintaining the Typhoon fleet required resources that became increasingly scarce as the Soviet economy deteriorated through the late 1980s. Each submarine demanded a crew of 160 highly trained specialists whose education required years of expensive technical schooling. Support infrastructure, including specialized maintenance piers, reactor servicing facilities, and weapons handling equipment, required constant upkeep and periodic modernization. The R-39 missiles themselves needed regular maintenance cycles and test launches to verify reliability. Security forces guarded the submarines around the clock. As economic pressures mounted and Cold War tensions eased following Mikhail Gorbachev's reform policies and engagement with Western leaders, Soviet and later Russian naval planners faced increasingly difficult decisions about which expensive systems to maintain and which to retire. The Soviet Union's collapse in 1991 effectively sealed the Typhoon's fate as an operational submarine force. The Russian Federation that emerged from the Soviet dissolution inherited a navy far too large and expensive for its drastically reduced economy to sustain. Shipyards lacked funds for repairs and maintenance. Personnel went months without pay. Nuclear fuel became difficult to source as supply chains disintegrated. Training schedules were abandoned. One by one over the following years, the Typhoons were withdrawn from active patrol status, though the decommissioning process stretched over more than a decade. Some were formally retired and laid up at piers with their reactors defueled and missile compartments emptied. Others remained nominally on the active roster but rarely left port, maintained by skeleton crews performing only the most essential preservation tasks. By the early 2000s, only one Typhoon remained in anything resembling active service. TK-208, the first of the class and the boat that had announced the program's existence by breaking through Arctic ice 2 decades earlier, was kept marginally operational primarily as a test platform for new missile systems under development rather than as a credible strategic deterrent asset. The other completed Typhoons sat deteriorating at piers in Severodvinsk, too expensive to maintain, but also too expensive and technically challenging to properly decommission and dismantle. The paradox of the Typhoon's size became apparent in retirement. The submarines that had been built to be invulnerable in operation became nearly impossible to dispose of when no longer needed. Dismantling a Typhoon presented technical challenges unlike any previous submarine disposal project. The twin nuclear reactors had to be carefully defueled with the spent fuel assemblies removed and transported to secure storage facilities. Reactor compartments had to be isolated and made radiologically safe. The massive hull had to be cut apart using specialized cutting equipment, a process complicated by the twin-hull construction and the sheer thickness of the steel. Radioactive components required careful handling according to protocols designed to prevent environmental contamination. Each complete dismantling operation cost tens of millions of dollars and required years to complete, expenses that cash-strapped Russian naval authorities struggled to fund. International assistance programs, funded partially by Western governments, concerned about nuclear security and potential environmental disasters from poorly maintained or abandoned nuclear submarines, eventually provided resources to begin systematically dismantling the retired Typhoons. The Cooperative Threat Reduction Program, also known as Nunn-Lugar, after its sponsoring American senators, allocated funding specifically for decommissioning Russian strategic submarines. The dismantling process revealed the extraordinary construction quality that characterized Soviet submarine building at its peak. The steel pressure hulls, even after decades of service including years of neglect, showed remarkably little corrosion. The reactor compartments were so robustly constructed that cutting through them required specialized plasma torches and days of continuous work. Workers who participated in the dismantling operations reported being genuinely awed by the scale and engineering sophistication they encountered, the massive machinery and redundant systems that filled spaces larger than buildings. The Typhoon's legacy extends far beyond its operational history into its lasting impact on submarine design philosophy and strategic deterrence thinking. It proved definitively that submarines could be built far larger than Western naval architects had considered practical or desirable, forcing complete reconsideration of size limitations in submarine engineering. It demonstrated that crew habitability wasn't merely a luxury or morale consideration, but a strategic necessity for submarines conducting extended deterrent patrols where crew performance directly affected mission success. And it stood as perhaps the most visible and dramatic symbol of Cold War military excess, a weapons system so enormous and so expensive that even its creators ultimately couldn't sustain it, built not because it represented the most efficient solution to strategic requirements, but because the Soviet Union needed to demonstrate capability to match and exceed anything the West could produce. Modern strategic submarines have deliberately not attempted to match the Typhoon's size. American Ohio-class boats, British Vanguard-class submarines, and the Russian Borei-class vessels that replaced the Typhoons in Russian strategic submarine service all displace roughly half the tonnage while carrying comparable or superior missile armaments using more compact and efficient designs enabled by advances in missile technology, materials, science, and submarine quieting. The Typhoon represented a peak of one particular design philosophy, the assumption that larger meant more capable, more survivable, and more prestigious. Subsequent experience and technological advancement demonstrated that smaller submarines with sophisticated quieting technology and advanced weapons could achieve strategic objectives more efficiently and at dramatically lower cost. Yet the Typhoon retains a powerful hold on military and popular imagination that more practical designs somehow lack. Its sheer scale, the audacity of building submarines that dwarfed surface warships, captures something essential about the Cold War's technological competition and the willingness of both superpowers to push engineering to its absolute limits. It represented an era when military requirements drove innovations that seemed impossible until they were achieved, when the shadow of nuclear annihilation hung over every strategic calculation, when nations built weapons of such power that their very existence seemed a form of madness, even as their purpose was preventing war. One Typhoon remains marginally operational in Russian naval service, kept barely functional through minimal maintenance, used occasionally for testing new technologies, or as a training platform where officers can experience the unique handling characteristics of the world's largest submarine. It serves as a living museum of Cold War submarine design, a connection to an era that feels increasingly remote. Naval officers from Western nations who have had opportunities to tour it report being impressed and somewhat unsettled by its vastness, by the visceral realization that this enormous machine once carried enough destructive power to end civilization, by the melancholy of seeing such an impressive engineering achievement reduced to a curiosity maintained primarily for nostalgia and occasional ceremonial purposes. Russian naval leadership has periodically discussed building new Typhoons incorporating modern technology, but economic realities and changed strategic requirements make such projects purely aspirational. The Arctic ice still covers the patrol zones where Typhoons once operated in silence, waiting beneath the frozen ceiling for launch orders that mercifully never came. Sonar arrays continue monitoring the depths, though the contacts they detect now are more likely research vessels and commercial traffic than military submarines. The Cold War's conclusion didn't eliminate nuclear weapons or strategic submarines, but it fundamentally changed the context, reducing the immediate existential threat that defined the Typhoon's operational environment and strategic purpose. The submarines that remain, whether laid up awaiting dismantling or preserved as monuments, stand as testament to an era of competition that consumed enormous resources and brilliant technical minds in pursuit of weapons systems designed never to be used. They remind observers that deterrence, while ultimately effective in preventing global nuclear war, required building machines of such devastating capacity that their very existence represented a kind of civilizational madness, a bet that fear and rational calculation would prevent their use. The Typhoon embodied this bargain in perhaps its purest form. The largest, most capable, most expensive submarine ever constructed, created to ensure its weapons would never need to be fired because potential adversaries understood the consequences would be unsurvivable. In the end, the Typhoons were paradoxically victims of their own success. They helped deter war so effectively that the political and economic system that created them collapsed before they could ever be tested in the combat they were designed for. They outlasted the Soviet Union itself, though barely, becoming artifacts of an empire that disappeared while the submarines remained, tied to deteriorating piers, too large to ignore and too expensive to maintain. Their legacy persists in strategic deterrence doctrine, in submarine design principles that subsequent generations of naval architects studied and often deliberately avoided replicating, and in the memories of crews who operated them, and intelligence personnel who tracked them with professional respect, tinged with relief that these weapons never fulfilled their ultimate purpose. The sonar echoes that once revealed typhoons prowling beneath Arctic ice have largely faded, replaced by different sounds, different threats, different competitions between nations. But somewhere in the cold darkness of the Arctic depths, in waters where sunlight never penetrates and pressure crushes anything not specifically engineered to withstand it, the memory and meaning of the Typhoon endures. The largest submarine ever built, the ultimate expression of Cold War deterrence, the steel leviathan that carried civilization's potential end within its hull and never had to release it. The deep thunder of its passage through Arctic waters has gone mostly silent now, but the legend remains, preserved in history like the ice that once concealed these giants, the final echoes of an era when superpowers competed in the ocean depths, and the world's fate rested with machines that moved through eternal darkness, undetected and unmatched, waiting for orders that would have meant the end of everything. They were built to ensure they would never be used, and in that they succeeded absolutely, disappearing not in nuclear fire but in economic collapse and strategic obsolescence, monuments to human ingenuity and human fear in equal measure, reminders that the most successful weapons are those that accomplish their purpose simply by existing, never firing a shot, deterring through presence alone until history moves past them and they fade into memory. The giants beneath the ice that kept the peace through the credible promise of annihilation.